Good day, everyone. Today, we're going to do SRT521, Assignment 1. It's a machine learning detector for malware. As we all know, malware is one of the biggest cyber threats these days and one of the most challenging use cases for machine learning. Pretty much, we will have to download dataset from Kaggle, right? And the objective of this assignment report is to create machine learning-based malware detector and to evaluate its accuracy. The goal is to conduct static analysis for the samples of the given malware, which is the dataset, to determine the best features suitable for different types of algorithm and how to extract them and to find most accurate algorithm that can distinguish the malware from benign samples with lowest error rate. I will use two different machine learning algorithms for this assignment report and compare their results. In this assignment report, I will show you some of the skills I learned from Lab 2 to Lab 6 to detect these malicious files in software accurately and timely by using machine learning algorithms using Python. So this is the file which I downloaded, the raw file. We've been advised not to use the integrated one. So yeah, this is the name of the file, and I have it here in my virtual machine, Ubuntu virtual machine. All right, and because as we know, machine learning only deal with numbers. Because as we know, machine learning only deal with numbers. So there are two primary approaches for malware detection: the signature-based and behavior-based heuristic analysis. The signature-based analysis used by antivirus software, which already had someone identify and uploaded the signature of the malware. So they have a database to refer if the file is again detected in the wild. They maybe just change the name, but that's how signature works. But we were going to do the behavior-based heuristic analysis, right? Heuristic analysis identifies malware based on deviation and expected normal behavior. For example, so we're going to use behavior-based analysis that focuses on the action or behavior of the program rather than its static signatures. It monitors how program interacts with the system and other processes. Heuristic analysis identifies malware based on deviation from expected normal behavior. And heuristic analysis is better detecting new or unknown malware but may produce false positive. Behavior-based analysis is essential for identifying new or evolving malware, but it may require more computational resources and can produce false alarm due to legitimate software behaving similarly. In this report, I will show you behavior-based heuristic analysis by means of using Kaggle CSV file downloaded that contains malware and benign features, and heuristic activity by using malware detection algorithm and machine learning technique using Python with several machine learning libraries and modules available. So with feature extraction, it is the process of selecting and transforming raw data into a set of relevant features for machine learning. It is crucial for dimensionally reduction and improving model performance. Okay, why reduce vector dimension? High dimensional data can lead to overfitting, increased computational cost, and decreased model generalization. Feature selection reduces the number of features while retaining the most informative ones, simplifying the model and improving interoperability. And selecting minimum numbers of features. The number of features should be determined based on domain knowledge, feature importance, and experimentation. Right, technique like recursive feature elimination or feature importance scores can help identify the most relevant. And so I created a Python program to extract features, as you see here. Right, and we will have to do the feature transformation, right? We will have to do conversion, cleaning, that's what I did earlier, and conversion. Normalization is scaling features to common range, adjusting it to 0 and 1, and standardization, scaling features to have 0 means and unit variance, and so on, right? So pretty much what I just been discussed there was also discussed in our lecture: hierarchical data, standardized data, normalized data, and binarized data for the machine learning to read properly and efficiently. So from those many features that I extracted, I just come up with just few and less compact CSV, right? And so moving to our program, pretty much this is the original file that I downloaded. There are a lot of noise, and yeah, this is the original one. And if you just come here, E1, just have a little bit, right? It's less and compact because it's already been trimmed, or like those technique that we did, normalization, etc. What I also did was I created a Python program just to read the original file before, and I just kind of like investigate which one is like not a number, and it outputted these two files just for my own information. But then later on, once I know that, I can like manually check it, or what are those fields that not a number. Yeah, so this is my program that collect features. So that's the one that outputted features txt, right? You see it there. Yeah, and as we move on to the next transformation of our database, I just have this view left as the title column left. So that's how compact my CSV now, which is this one, right? I also started with this one, and I improved it to this one, V1 and V2. So I will show you how these two can affect the result of the machine learning algorithm output later on anyway. moving on to training the model, I picked the following supervised machine learning algorithm and train my model using that data from previous base. To train my model, I will use to supervised machine learning, J48 decision tree, and SVM, right? So here's my simple Python program that does that, and so we'll see it in action. As you can see, guys, we split the data to X train and Y train, and then the J48 decision tree, right, and the prediction, right, and same as the SVM train vector machine, and then the prediction, and let's see it in action. Okay, so we have the J48 have 0.92 accuracy, and the SVM have 0.74. Okay, moving on to cross-validation. ML algorithms cannot predict the accuracy of the result, and hence they need to be cross-validated with new data. Cross-validation is a technique to assess model performance and generalization by dividing the data into subsets. There are 3 different classes of cross-validation, using them to validate each of your training models. The main idea is to divide the data into different sets, such as training data, validation, and test data. The main method includes holdout method, splitting data into training set and testing set. Simple way to estimate model performance, but may vary based on the random split. K-fold method, data is divided into K-subset folds. The model is trained and tested K times, and using each fold as a test set 1. This provides more reliable estimate of model performance. Leave one out method is each data point is used as a test set once, while the remaining data points are used for training. It's resource intensive but provides unbiased estimate. So below is a program that provides cross-validation using 3 methods, as mentioned above, right? Okay, guys, so I ran it before, so let's see this in action. Okay, so cross-validation, as you see here. This is the holdout method. We split the into X train and Y train also, and here's K-fold. Right, we will print this one later. I'll show right here. Actually, I already run it. Holdout. And here's a K-fold method, right, and the leave one out method. So as I run it, I said earlier, it is resource intensive usage. So you see, guys, I ran it already, but the last one is not running because it's still processing. But pretty much you can see the holdout method accuracy is 0.95 or 96 if you round that up, and for K-fold method average is 0.94 accuracy. Finally, it's finished processing, and for the leave one out method, we have accuracy of 0.94. Finally, guys, we will have to do the improved results by calculating the accuracy and false positive rate for each of my model and try to improve it. I can improve the result by tuning hyperparameters to optimize the model performance and feature engineering to create more informative features and regularizing the model to prevent overfitting, and ensuring appropriate data processing, cleaning, and transformation, as we did earlier, using ensemble methods like random forest and boosting to combine multiple models, and evaluating model performance using appropriate metrics, visualizing results, model interpretation, insight, and model behavior. I will illustrate this concept by taking simple dataset, building classification model with SVM, and tuning hyperparameters using feature selection, applying cross-validation to assess model performance in Python. Below is a program that demonstrates how to improve results and classification model using a specified concept. This example uses the SVM classifier and tunes hyperparameters, employs feature selection, and applies cross-validation to assess performance. It also includes visualization and comment for better understanding. And so, yeah, this is my Python program, right? This script starting point, and I need to adjust hyperparameter with feature selection method or details based on my specific dataset requirement and the code. The program performs evaluation using holdout method that applies feature selection, hyperparameter tuning to improve SVM model, right, as you can see there. So actually, when I ran that program, that A17 improved results graph.py, it took a long time to process, and the code I updated to make it processing execution quick as possible. I leave it for 2 days running, guys, and it's not stopping. I use 4. I will show you. I use 4 processors there too, and so on, and it's still not working fast. It's like like 2 days is still not stopping to process. So if I have a supercomputer, maybe that's good. So so finally, I will show you this in action. This is the program that I created earlier, and actually this one have 10 like that, and I lower it, and I use 4 processor already, but it's taking a long time to process, and I'm not getting any result. Like, I'm getting just part result, but not all. And so I improve it over here and trim some of unnecessary, like a thing that make it really long to process, right? As you can see, feature selection, hyperparameter tuning is here, like we discussed it in our lecture, and cross-validation using SVM model and so on. But what I come up with is this, actually, and so this runs faster as much as possible, and I can play around with the parameters here. You know, the CV means here is that means that the dataset will be divided into 30 part fold. The training and the validation process will be repeated 30 times, with each fold used as a validation set exactly once. The performance metric accuracy in this case is then averaged over these 30 runs. Okay. So the only reason I did that is to actually basically get the optimal results. So we want to improve results, right? Other than that, I also use this V2 of my V1 and V2. I can show you a big difference, right? So I'm going to talk about the graph later. Yeah. So as you can see right now, this is the version 2 of my file, CSV file, and this is what we achieved. Let's see if we put it to V1 actually, and see if it will improve. We're going to save it and then run it. So by actually, what I'm trying to show here to another improvement is by changing the input data set. It can change the result also a little bit, but you see, if I use the V2, you get less, right? And when I use the V1, I have 0.93. So it also depends on how clean the dataset input is. It can improve the result. This is what I observed. So as you can see, there's this one, and then I evolved to this one, and then finally this one is the one that I convinced that it's not really, you know, it's doing its best, but I can run it right away, and then I can play around with the parameters too. So by this is the optimum that I get, right? 0.94, and in the initial holdout method is 0.70, right? And what I've done here, guys, is actually change this, right, from 2 to and then the CV, you know, the CV, okay, finally we have the presentation of results. So use graph. All right, and so we'll have to evaluate and the tuned model using cross validation, and visualizes the result with confusion matrix heat maps. It creates the display and heat map of the confusion matrix, providing visual presentation on how well the SVM model performs on the test set. And the color intensity in the cells indicates the frequency of correct and incorrect prediction. And here's the graph, guys. And let's see this one in action. Okay, let me run this thing. So you can see the confusion matrix 5 and 5 and 1 and 9. From predicted is 1 and 9, actual 5 and 5 over there, right? And that's for the confusion matrix holdout. And let's see for the SVM model cross validation, right? For 30 folds, this is how accurate that we met over there, right? And that's why we come up with this result with the cross validation accuracy. So thank you for watching, guys, and I hope you enjoyed watching my video, and have a nice day. Thank you. Bye.